Good morning, guys. Today we're going to talk about real numbers and writing mathematical operations. Okay. The first thing we're going to talk about is the real number system. Okay. We have different classification for real numbers. Okay. Real numbers are pretty much every single number that you guys are used to. Okay. The first set of numbers we're going to talk about are natural numbers. Okay. Natural numbers are our counting numbers. Okay, our counting numbers. And what are our counting numbers? Well, we start with 1, then we go to 2, 3, 4, and so on. So if I ask you the number 7, is that a natural number? Yes, it is, because we can count to 7. Okay. The next one are whole numbers. Whole numbers are actually all of your natural numbers plus one new number, and that is 0. So it's 0 and your counting numbers. Okay, so as you can look, the numbers 1, 2, 3, 4, and so on were natural numbers, but they're also whole numbers. The only difference is 0. Okay, so your whole numbers are 0, 1, 2, 3, 4, and so on. Okay, so if I look at this Venn diagram here, you guys have all seen Venn diagrams. Okay, I'm going to start with this square represents every single number that we've talked about, real numbers. Okay, now if you notice, every single natural number is a whole number except for 0. So when we throw it into the real number system, I'm going to put natural numbers here in the circle, okay, in this circle. And all of these natural numbers are whole numbers. So I'm going to draw it kind of like a donut. That whole number is going to go around natural numbers because every single number I put into natural, like 1, 2, 3, and so on, is also a whole number. The only number that is not the same is 0. So 0 is the only number that goes in just whole and not natural. Okay. The next one are integers. Okay. Integers are all of their whole numbers. So all whole numbers and their opposites. And their opposites. Okay, so if it says all whole numbers, that means you're going to have 0, 1, 2, 3, and so on. They're opposites. 0 doesn't have an opposite because it's neither positive nor negative. It kind of splits the two. The opposite of 1 is -1. The opposite of 2 is -2. The opposite of 3 is -3. The opposite of 4 would be -4. So everything else that way. Okay, so integers are all of the whole numbers and their opposites. So are all integers natural numbers? Yeah. Okay, so all natural numbers are integers. So if I go to the Venn diagram, I'm going to put integers on the outside here because integers are all whole numbers, all natural numbers. The only numbers that are different are those negatives. So we'd also throw in like -3, -5. Those are the ones that are integers, but not necessarily whole or natural. Okay. Now, if you notice about natural, whole, and integers, those are all numbers without decimals, fractions, anything like that. Now, every real number is either classified as rational or irrational. Okay, so rational or irrational. Your rational numbers are all of these numbers here. Okay, are all of those numbers. So it's going to have your natural numbers, your whole numbers, your integers, but these ones do include decimals that end. So rational numbers are those decimals that end or repeat, And the reason why those include decimals that end and repeat, because the main thing is they can be written as fractions. So the reason why rational numbers are numbers that can be written as a fraction. Okay, if I look and I said natural, whole, integers, those are rational numbers because if I look at the number 2, I can write that as a fraction, 2 over 1. I could take 4 and write 4 over 1. Same thing with your negative. I could have negative 2 over 1. Decimals that end, like 0.5, we all know is 1/2. That can be written as a fraction. Okay, so decimals that end or repeat. If you look at 0.3 repeating, we all know 0.3 repeating is 1/3. Again, can be written as a fraction. So examples of rational again is like 1, 2, because we can write them as fraction. You could have 1/2. You could have 2 3/4. You can have negative 2 3/4. You could have 0.25, okay? 0.6 repeating, things like that. So again, we said natural, whole, and integers are rational numbers. So if I look at my Venn diagram, I'm going to actually put rational numbers on the outside because every natural, whole, and integer is rational. But we do have numbers that aren't natural, that aren't whole, that aren't integers, that are rational, such as like 1/2, negative 2/3, things like that. Now, if a number's not rational, it is known as irrational, okay? Irrational numbers, okay, are numbers that never end or repeat. Okay? Sorry, so they're never end or repeat. So biggest one, pi. Pi is 3.1415926, and so on. It keeps on going, never ends, nor never repeats. Okay. Other ones would be like the square root of 5. Okay, I can't take the square root of 5. Actually, that's an irrational number because the square root of 5 is a decimal, like 2 point something that goes on and on forever, never ends, never repeats. So if this is not a perfect square, you can't take the square root of it, meaning it's going to be an irrational number. So once again, I said numbers can't be rational and irrational at the same time. So if all of these are rational here, sorry, irrational is its own category. So like the square root of 10, square root of 52, okay, pi, 2 pi, okay, things like that. Let's go ahead and classify these numbers. Okay. 36. All right, so I always kind of go with, is 36 rational, whole, or irrational? Automatically, is it rational or irrational? Can 36 be written as a fraction? Yes, it can. So that would mean it is rational. Okay. Now, if it's rational, we have to double check. Is it natural? Is it whole? And is it an integer? Natural numbers are your counting numbers. Can I count to 36? Yes, I can. So that's a natural number. Whole numbers are your counting numbers and 0. Well, we counted it, so it is also a whole number. Integers are whole numbers and their opposites. Well, it's a whole number, so automatically has to be an integer also. Okay. All right, B here. Square root of 32. Is 32 a perfect square? Can I take the square root of 32? No. So then I ask, well, is it rational or irrational? I can't take the square root of it. So if I can't take the square root of it, can I write it as a fraction? No. So that would be irrational. And since it's irrational, it can't be anything else. Right, negative 2.6. So it has to be either rational or irrational. Okay? Can I write 0.6 as a fraction? Can I write 0.6 as a fraction? Yes, because that's in the 10th position because it's an ending decimal. So it'd be 6 over 10. So yes, I can. So So we know it is going to be rational. Okay? And then we ask ourselves, if it's rational, is it natural? Can I count to negative 2.6? No, we normally don't do that. Okay. Is it a whole number? Is it a counting number in zero? Well, we're not going to count it, and it's not zero, so it can't be whole. And then integer, is it a whole number and its opposite? It has that decimal, so it cannot be that. So it's just rational in this sense. Okay. And then negative 6. Is it rational or irrational? Can I write negative 6 as a fraction? Yes, I can. So we know it's going to be a rational number. So now let's go through. Natural. Am I going to count to negative 6? No, I only count to 6. Is it a whole number? So is it a counting number and 0? I don't count to negative 6 and it's not 0, so it can't be whole. Now, is it an integer? Is it a whole number and its opposite? So this wasn't a whole number, but is it an opposite of a whole number? Yes, it is. This is the opposite of 6. So this would be a integer. Okay. All right. 7/2. Okay. So is it rational or irrational? 7/2, it's a fraction. So can I write it as a fraction? Yes. So we know it's going to be rational. Now it's a fraction, so would we count it? No. Would it be a counting number in 0? No. An integer, is it a whole number or its opposite? This is not a whole number because it's a fraction. So this one is just a rational number. Okay. All right, so square root of 81. Is it rational or irrational? Well, can I take the square root of 81? Yes, I can. It is 9 because 9 times 9 is 81. So we're looking at 9 technically. So is 9 rational or irrational? It is rational because we can write it as a fraction. Can we count to 9? Yes. So that means it would be natural. Can we count it or is it 0? Yes. So that would be a whole number. Is it a whole number or its opposite? It's a whole number, so it's also an integer. All right. If you have any questions about real numbers classifying, please, please, please let me know. Okay. Now what we're going to do is we're going to estimate that irrational number. So like square root of 81, we could take the square root of that. So that's pretty easy. So now classifying or estimating, like the square root of 5, like I said. I can't take the square root of 5 because there's no two numbers the same that multiplies by 5. Okay, so what we're going to do is we're going to look at our perfect squares. Okay, what are our perfect squares? Well, let's start with 1. What's 1 times 1? 1. 2 times 2, 4. 3 times 3, 9. 4 times 4, 16. 5 times 5, 25. 6 times 6, 36. 7 and 7, 49. 8 and 8, 64. 9 and 9, 81. 10 and 10, 100. 11 and 11, 121. 12 and 12, 144. 13 and 13, 169. 14 and 14, 196. And 15 and 15 is 225. So these are our perfect squares. And they're not all of them. I only went to 15. But what we do when we're trying to estimate this, we're going to find the perfect square that this number is in between. Okay, so if I look at 5, 5 is in between 4 and 9. Okay, then I see which perfect square is the number closest to. So is 5 closer to 4 or 9? Well, it's closer to 4, right? Because it's only 1 unit away from 4, but it's 4 units away from 9. So it's closer to 4. And we're going to take the square root of the one it's closest to. So the square root of 4 is 2. So we'd say that's approximately 2. So what that means, the square root of 5 is roughly like 2.1, 2.2, 2.3. So if we actually rounded it, it would round down to 2. Okay. All right. So let's look at the square root of 32. All right. 32 is in between what two perfect squares? So if I look at 32, I'd say it's in between 25 and 36. So it's in between 25 and 36. So now we look at which one is it closer to. Well, 25 to 32 is 7 units. 32 to 36 is 4 units. So which one is it closest to? It's closest to 36. So we're going to say the square root of 32 is approximately, what's the square root of 36? 6. So meaning that would have been like 5.6, 5.7, so that we would round up to 6. Okay. All right, and then the last one here. Okay. 112. What is 112 in between? 112. I see 100 and I see 121. 100 and 121. So 100 to 112 is 12 units. 112 to 121 is 9 units. So which one is it closest to? 121. So we're going to say the square root of 112 is approximately, what's the square root of 121? 11. Okay. Moving on. All right. Now, writing expressions. Okay. So what are some words that represent addition here? This is a plus sign. So we could use sum plus increase, increased by, add, addition, in total, things like that, okay? Remember, sum represents the answer to an addition problem. The next one, this minus sign, say minus would work. Decrease or decrease by, subtract. Let's see what else. Less than, and there are more. The answer to a subtraction problem is not sum is addition, it is difference. It's the answer to the subtraction problem. Okay. All right, next one, this little dot represents multiplication. So multiply would be a good one. Times. Twice. Twice a number means 2 times. Okay. Triple of would be a good one. Double. The answer to a multiplication is product. Product, that's a U there. The division sign, as we just talked about, division, divide. Per is a good one. Split. Split. Half. Okay. The answer to a division is known as quotient. And then the parentheses, quantity. Is a good one for quantity. Quantity. Okay. Now, what we're going to use this is we're going to have mathematical sentences, okay, mathematical words, and we're going to have to put it as an expression. Okay, an expression uses numbers, variables, and operations. Expressions have no equal signs. So an expression could be like 2x plus 3, 7 plus 9 divided by x, things like that. Okay. X over 2. All right, so let's go ahead. We're going to write an algebraic expression from the words now. Okay. Product. Product means the answer to a multiplication problem. So we're going to multiply a number. So we're going to represent, we don't know that number. So we'll label it x and 7. So we have x times 7. You could also write it as 7x. All right, B here. Twice. Twice means 2 times we're doubling something. Now, the sum is the answer to the multiplication or the addition problem. So the answer, we want to take twice the answer. And if we want to take the answer and double it, if I want to add first, I have to put parentheses around it. And a number would be like x plus 3. So twice the answer to the adding. So we need to make sure we can add before we can multiply. Okay. All right, the quotient. The quotient. Quotient is the answer to a division problem. So what is the answer of the division problem? 12 and a number. So we're going to take 12 divided by a number, so x. Now, I could put parentheses around it because we want to make sure we do the quotient first to get the answer, then add 9. However, with division, we always divide before we add. So we could have left it as 12 over x plus 9. You could also use 12, the division symbol, x plus 9. Okay. All right, the next one. 15 times a number decreased by 6. So this one, there's no answer to anything, so we're just going to go in order. So 15 times a number, x, decrease means minus 6. Okay. Now, make sure if you see less than and less, you pay attention to what it's asking for, okay? Because if we're looking at 5 less a number x, okay? 5 less a number x just means we're taking 5 minus x. Now, if I would say 5 less than a number, we're taking 5 away from that x. So it's x minus 5. So make sure less than, you're going to switch that order unless you keep it as the order it says. Okay. Okay, so that's algebraic expressions, writing them from words. The last part is our properties. Okay, and we have properties for both addition and multiplication. Okay, so I'm going to show them. I didn't write them all individually for you, but we're going to write them all. Okay, so the commutative property, it takes two numbers and says it doesn't matter the way you add them or multiply them, it's going to be the same. So if I take A plus B, it's the same as taking B plus A. Yeah, because if I take 2 plus 3, isn't that the same as 3 plus 2? And then same thing with multiplication. If I take A times B, it is the same as B times A. 5 times 2 is the same as 2 times 5. Okay. The associative property, okay, is now taking 3 numbers and switching the order. Okay. So with that, I'm going to take A plus B, then add C. That is going to be the same as if I do B plus C first, then add A. If you notice, I put A plus B plus C. It's the same in both of those, but the parentheses tells me I have to do that one first. Okay. I can take 2 plus 3, then add 5, and it's the same as taking 3 plus 5, then adding 2. Okay, you're taking the same 3 numbers and adding them. Same thing with multiplication. I could do A times B, then times C, or I can do B times C, then times A. It's always going to be the same. Okay. The identity property. When you think of identity, or at least when I think of identity, I think the same thing. ID, that's me. Okay? So if I take a number and add something, I need to get back to myself. Okay? So if I take 2 and add it to what would get me back to 2? 0. So the identity property of addition is a number plus 0 is its number. Okay? Multiplication, same idea. A times what gets me back to A? So 3 times what would get me back to 3? 1. Okay. All right, and then inverse. Inverse is like our opposite, okay? So if I take a number, add it to something, instead of getting it back to its identity, we get it to 0. So A plus what would get me to 0? 3 plus what would get me to 0? Its opposite, which would be -3 or negative a. So the inverse of addition is you add a number plus its opposite will get you to 0. Okay. Inverse for multiplication is a times what gets me to 1. Okay. Think of 2. 2 times what would get me to 1? Well, you know 2 divided by 2 is 1. Instead of dividing, I want to multiply. So think of fractions. When you divide, you can't divide fractions. You keep it, you change it, you flip it. So you keep it, change it, flip it. So you actually multiply by its reciprocal, which is 1 over a, or 1 over 2. A half of 2 is 1. Okay. Now, the last property is the distributive property. We'll hit this one a lot more later on. Okay, we have actually a whole unit on that. The distributive property is the only property that doesn't have just for addition or just for multiplication. And the reason being is because it actually includes both a times b plus c or a times b minus c, and it also includes multiplication. Okay. The distributive property says if I have a number on the outside of a parenthesis and it's multiplication, I can multiply that number by everything on the inside, and it's going to be the same. So I could take a times b plus a times c. So if I multiply a by both of those numbers and then add it up, it's going to be the same. And it goes the same if it's a subtraction. I'm going to take a times that b, but instead of adding a times that c, I'm going to subtract because a positive times that negative is a negative. Okay. So let's identify our properties here. All right, so we do have 3 numbers, okay? So we always look at anytime it's adding, subtracting, and it's kind of looking at parentheses or numbers in that sense, we always look at, is it commutative or is it associative, okay? So in A, we are going to add 3 plus 4, then add 7. This one, we're going to add 3 plus 7 first, then add 4. So we're switching the order of 3 different numbers. So if I'm switching the order of 3 numbers, would that be commutative or associative? I think it would be associative. So we're going to say this is the associative property, and I'm going to abbreviate. We always do 5 letters. This is the associative property of, this is adding, so we're going to say of addition, and I'm going to put a plus. Okay. All right, the next one here. Now we have 3 numbers again, 3 numbers. And so we're going to look at associative or commutative. And now let's look at this. We're going to take 4 times 3, then times 6. Then we're going to take 3 times 4, then times 6. So in this case, the 6 is still the last thing we multiply. So that's not changing. But what's changing is the order of just the 3 and the 4. So we're just switching the order of 3 and 4. So now would that be associative or commutative? Because it's only switching the order of 2 numbers, that one would be commutative. And is this the commutative property of addition or multiplication? It is multiplication. Okay. All right, next one. 4 times 1 equals 4. 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 All right, so we're taking 4, timesing it by 1, and getting it back to 4. So I'm getting it back to itself. And if it's getting back to itself, it is the identity property. And this is multiplication, so it's of multiplication. All right, the next one, we're taking 6, adding a -6, and we get to 0. So we are not getting back to itself. So that is not the identity. But I am taking a number, adding its opposite to get to 0. So when we add its opposite, it's known as the inverse. So this is the inverse prop of addition because we're adding. All right, next one. 5 plus 0 equals 5. So we're ending back up with exactly what we started with. So that since we're ending with itself, this would be our identity property. And this one is of addition because we're adding it. And then that last one, 2/3 times 3/2 equals 1. So we're starting with a number, multiplying by its reciprocal, and getting to 1. So it's not identity because we're not getting back to itself, but it's taking its reciprocal and multiplying it to get to 1. So that one would be our inverse property of multiplication. Okay. Now, if you guys have any questions whatsoever on this, please, please, please let me know. Okay, email me, set up a Google Meet, anything like that. Okay, thank you.